Okay, so let's move over now to a more systematic approach to determining the stiffness coefficient Kij of a system or a structure. And I'm going to use the virtual work method to deal with this. Although there are a lot of methods used, you can use the mechanics approach, you can use the classical solution slope deflection method, work energy, although this is a work energy solution, so there are other work energy equations that you can do to formulate your structure stiffness coefficient Kij. So for an elastic system in equilibrium, the work done by the external forces is equal to the work done by the external force multiplied by a virtual displacement. So that is actually the definition of how your virtual work method is used. Okay, so WE is equal down to Kij delta J, and note that J corresponds to the DOF upon which the virtual displacement delta is assigned the value equal to 1. For the consideration of the internal work done or performed, we have to bear in mind that your beam problem is a flexural member, so the bending moment is the key equation to consider when it comes to the internal work, and the internal work is actually the summation or simply the integral of all the moment, the internal moment uh, induced in the beam from within the domain 0 to L. Okay, so and those moments should be individually multiplied by a generalized displacement in terms of an actual rotation, which is a result of the virtual displacement assigned to it equivalent to 1. So mx we have already obtained from the above differential equation, so we can use this formulation, this differential equation, uh, as your working equation to solve for the uh, uh, solution, no, in determining your stiffness. And ux is actually an approximation of your njx. So this is an approximation of ux. So we can actually substitute in place of ux here your njx, such that your uh, second derivative of ux is simply equal to the second derivative of njx. So this is just shown in terms of a double prime symbol. Okay, so and consequently your moment now, which is this one, is simply ei times n double prime jx. So you have now your derived formula for mx in terms of the shape function, and of course your material and dimensional inertial properties. So upon which your internal moment now becomes simply the integral from 0 to L, or sorry, the internal work performed or done is now the integral from 0 to L of ei times n double prime j x multiplied by d theta, and equating your wi with the external work, and noting that d theta is simply the angular displacement produced during this virtual displacement. It's actually related to the resulting transverse deflection given by the shape function nix, whatever is that shape function. Your d theta will actually inherit it. So such that from a definition of theta, we know that theta is a slope equivalent to du dx, and the derivative of theta with respect to x now becomes the second derivative of u with respect to x squared. Okay, so where ux again approximated by the shape function will yield to a d theta dx equivalent to a, second derivative of nix with respect to x squared, or simply n double prime ix. And d theta upon multiplying by dx on both sides will yield to n double prime ix dx. So that finally the stiffness equation now becomes simply a kij is equal to the integral from 0 to L ei n double prime ix times n double prime jx, okay, dx. Okay, so upon substituting d theta and equating it to your um, external work done, which is kij. Okay, so here we actually equated we and wi, because this is simply kij times 1, which is your delta, is equal to the integral from 0 to L of ei, okay, your uh, n double prime of x, which is your d theta, times your n double prime j of x, which is your moment. Okay, so this is now dx. Okay, so simply this part here constitute your d theta, and this part here constitute your mx. Okay, of course kasama siya dito sa d theta. Okay, yung d theta ni double prime. Okay, so let's have an illustrative example on how to determine K11. So using this equation, so this is our working equation. In your finite element analysis, you will be using the same. Okay, I hope those who are finished finite element has already gone through a lot of simplifications of this local stiffness matrix. This is an element matrix, so it's still a localized stiffness matrix. And for the illustrative example, we ought to determine K11. We simply plug in what is, sorry, this is 1. Okay, so determine K11, we simply plug in I equals 1, j equals 1. Therefore, your K11 becomes N1, N1. Okay, so we just put it there. And then looking into your equations above, we have derived, okay, we have derived this 1, 2, 3, 4 equation. So this is your N1. I just plug in what is my N1, this one. Okay, N1 is this one, N1, 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 so it's just a squared. Okay, so fortunately I use MathCAD to simplify things because I don't want to simplify it manually anymore, so I guess simply get 12e over L cubed. So that's the good thing. You need to have a tool in order to facilitate your problem set computation. If you want to experience hell every time I give problem sets, then don't mind studying MathCAD or MATLAB. Okay, so for your sorry class, again correction, it's a cut and paste error. This is a K11. Okay, so for your K12 illustrative example, K12, I equals 1, j equals 2, we have a K12, N1, N2. So this is my N1, this is my N2. Okay, so I simply take the derivative, the second derivative. So I just plug it there, I plug it here, and then boom, integrate it, I get my value. Okay, so if you are doing a case study, a research, or any problem set, and you don't know how to use these tools in your master's degree program, I doubt if you can last for so long, because you're wasting a lot of time doing it manually. But if you're good in math and you want to practice it, I don't think it's a problem at all. Okay, so determine K22, we get note I equals 2, J equals 2. Again, plug in N2 double prime, N2 double prime. So you just make a second derivative of your N2, you get this one, then plug it there, you get this one. Okay, so see how it works. And K24, you get I equals 2, J equals 4, K24 is this one. N4 double prime is the second derivative of N4, and this is now your N4. Okay, N2, this is your N2 as derived a while ago. You plug N2 and N4 there, you get your. In short, the stiffness matrix can be easily obtained by doing this procedure, and as you can see from a lot of references, the local stiffness matrix of an element, a beam element, which is oriented. Okay, so this is oriented horizontally. So this is horizontal, meaning to say your theta equals 0 is this one. Okay, if the angle of the beam is inclined at an angle of, say, theta, you have to make use of a transformation rotational matrix R, K transpose K Ij R. Okay, so you just make use of this transformation rotation matrix in order to get a value of your local stiffness matrix, and you will see there a sine cosine something along the way. Okay, so the total force P1 at the coordinate 1 resulting from this nodal displacement is simply obtained by the superposition of the resulting forces, and that is P1 is simply K11 delta 1 plus K12 delta 2, K13 delta 3 plus K14 delta 4. Okay, so it's a pk delta value. Okay, so we take note of this, and for P2 you just substitute K21, K22, K23, and K24. This is actually the first row of K's of K I J. This is the second row of Kij, and this is the third row and this is the fourth row of Kij. Okay, such that this is the first, second, third, fourth. This is the vector delta in matrix form. You have this as your, what do you call this? This is the stiffness equation. Okay, remember that these are generalized forces. So this is a value of a force P, let's say P at I end. This is a moment at I end. This is a P at J end, and this is a moment at J end. Okay, so what I mean is if I go back to my original equation, so this is my I node, this is my J node. Okay, so this is my P I, this is my M I, this is my PJ, this is my MJ. So they are generalized in the sense that this can be a force and a moment. At this point, this is also generalized. This is actually your what do you call this, displacement in terms of delta I, and this is a theta I. Okay, delta J, theta J. So something like this. Okay, in condensed form, you can use a formula such as this one. So P vector is equal to K matrix times delta vector. Again, this is your stiffness equation. Okay, so in the next video, I will be discussing to you how to assemble these matrices, these local matrices using the simple procedure I taught you last time on connectivity principle. Okay, that's all for now, guys. I'll see you in the next video.